Hello there. In this video, I am going to be developing the concept of the definite integral by looking at area under a curve. So this video is just meant to be somewhat of a review of these concepts for my Calc 2 students. So you've already had the idea of area under a curve and the definite integral. So this is just meant to be a video to kind of quickly review and tie in these different ideas. Because as we move through Calculus 2, we're going to be coming back to this concept of the area under a curve developing a definite integral for different applications. So let's just start with a graph of a function. So just going to make a quick little graph here. And we'll just make it something simple, something like this. We don't really care what the function is. I'm not going to be using any actual numbers. This is just going to be kind of a theoretical development. So what we want to do is we want to find the area underneath this curve between the y-axis, which would be x equals 0. Let's call that our a value. And this point right here on the x-axis, let's call that our b value. Well, we don't know how to find the area of an irregular area. We can, however, find the area of a rectangle. We know that a rectangle, the area, is equal to the length times the width. So we could call this the width, we could call this the length, and the area of that rectangle is the length times the width. And so what we're going to be doing is we're going to be using rectangles to find the area underneath this curve. So let's just start by using two rectangles. All right, so what I'm going to do is I'm going to start right here at A, and I'm going to make a rectangle that kind of divides the area in half. And then I'm going to go here and make another rectangle that goes to B. All right, so I've created two rectangles. Now notice that the area under the curve is completely contained within these rectangles. And the area between A and B has been divided evenly. And so what I'm going to do, since this is the x-axis, I can call this distance here, let's go to red. I'm going to call this distance here delta x. It's a change in x. And so this is also delta x. Well, if I want to find the area of these rectangles, I'm going to use the formula length times width. Now, how do I find the length of the rectangle? Well, the length of the rectangles is basically the height of the rectangle. And to find the height of the rectangle, what we need to do is we need to find out where does the top of the rectangle intersect the curve, okay? And so the curve here, basically, let me write that, is f of x, that's our function. And so it intersects right here. So to find the height of this rectangle, what I really do is I'm going to find the height of that rectangle at that particular point. And so let's just call that a is equal, let's just call that x sub 1 right now. And then let's call this x sub 2 right there. And so the height of the rectangle is the function value at x sub 1. So we would evaluate that function at x sub 1. All right, so I can put this here. This is f of x sub 1. Why x sub 1 again? Because x sub 1 is this point right here where it is touching the curve. Well, the second and the width of the rectangle is delta x. So finding the function value at x sub 1 and multiplying by delta x gives me the area of this first rectangle. Well, the second rectangle is going to be the function value at x sub 2. Again, why x sub 2? Because right here at x sub 2 is where the rectangle intersects the curve, right? So if we go over, this value right over here is going to be f of 2. That's the function value at f of x sub 2. And so the width of the rectangle is once again delta x. Now, to find the total area under the curve, we simply add these together. Now, this would then be equal to the total area. We can say A sub t, the total area of that. And what we want to do is we want to come up with a little bit more precise notation for this, because what we're doing is we're doing a sum here, and we're adding together this product of f of x sub 1 delta x, and we're adding f of x sub 2 delta x to get the area under the curve. And so the notation that I'm going to use here is I'm going to use what is called summation notation. You've probably seen this before. From I equals 1 to 2. Why 2? Because I have two rectangles. I'm using x sub 1, x sub 2. So remember, I is an index. And so what it basically, think of it as when I is equal to 1, we're using x sub 1. When I is equal to 2, we're going to go over here and use x sub 2. And so what we're doing is we're finding the summation of I from 1 to 2 of f of x sub I times delta x. So what that's equal to is the above sum, f of x sub 1 delta x plus f of x sub 2 delta x. Now, this has a name, and you probably will remember this. You've heard it before. It's called a Riemann sum. Yep, a Riemann sum. And so the Riemann sum is simply a notation that we use that says, hey, we're taking all of these products and we're adding them up. That's why it's called a Riemann sum, and we use summation notation. And so the total area would be approximately equal to this. Well, we can see a flaw in this whole system here. And the flaw is that we have all of this excess area over here and all of this excess area here that's not under the curve. It's actually above the curve. So when we find these areas here and add them together, we're going to have too much area. It's not going to be the area under the curve. It's going to be the area under the curve plus all this highlighted green area. So it's really not very accurate. Well, as it turns out, what we could do to make this more accurate is use more rectangles. So what I'm going to do now is I'm going to repeat this process, but now I am going to use 4 rectangles. All right. So again, we're going to use 4 rectangles. And so it doesn't really matter where, there we go. Pretend those are all the same width, all right? So the width of each rectangle is delta x. And so let's call this, so where does the first rectangle intersect? Let me go to red. So we have, this is going to be my x sub 1. And right here is where rectangle, this is rectangle 1, rectangle 2, rectangle 3, rectangle 4. And so rectangle 2 intersects at x sub 2, rectangle 3 intersects at x sub 3, rectangle 4 intercepts at x sub 4. Now in both of these, I made the left endpoint of the rectangle touch the curve, but it doesn't matter. It could be the right endpoint, it could be the midpoint, it could be any point, theoretically, on the top of each rectangle. And so let's go through and calculate the approximate area again. So the area is going to be equal to f of x sub 1 delta x plus f of x sub 2 delta x plus f of x sub 3 delta x plus f of x sub 4 delta x. And to write this as a Riemann sum, we can say that the total area is approximately, because I should be using approximately equal to here, is the summation from I equals 1 to 4 now, because we're using 4 rectangles, of f of x sub I times delta x. Well, we can see a problem here again, right? We still have excess area. I have this area here, and this area here is excess area. Now, depending on where the rectangles intersect the curve, you could have too little area. But in this case, the way that I'm doing it, we always have excess area. And so if you take a look and compare that excess area there to the problem we did before, we have less excess area. I would say that the green area up here is greater than the green area that we have in this second example. And so, let's see. So we're going to get a closer approximation to the actual area under the curve, but we're not going to get the exact area under a curve. Well, if we carry this thought process further and further, if using 4 rectangles to calculate the area under the curve was more accurate than 2 rectangles, then perhaps 8 rectangles or 10 rectangles would be more accurate than 4. And as it turns out, that is true. And so if 10 rectangles is more accurate than 4, then 100 rectangles would be even more accurate. Or what about 1,000 rectangles? With 1,000 rectangles, we're going to have a really accurate area under the curve. We're going to have very little excess area, very little of that highlighted green area. But there'll still be a little bit. So no matter how many rectangles we take, we're always going to have a little tiny bit of excess area unless we make the number of rectangles infinitely large. Can we do that? And the answer is yes, we can. We can use a concept, an old friend of ours from Calc 1 called the limit. And so what we're going to do now is, again, let's think through this through. We're looking for the area, the total area. And what we want to do is we want to take our Riemann sum from I equals 1 to, this time I'm going to let it be equal to n. N is maybe 10, maybe is 1,000, maybe is 1,000,000. N is some number of rectangles. We don't know how many rectangles now. But what I do know is I want to take the limit as n approaches infinity. If I let the number of rectangles get infinitely large of my Riemann sum, then as it turns out, this is not an approximate area, it is the exact area. So A sub t is equal to the limit as the number of rectangles approaches infinity. So this is a very important little formula here. This is a Riemann sum that will give us the exact area underneath a curve. The problem is, how do you calculate the area of an infinite number of rectangles? And this is where we tie it into the definite integral. Because this formula, and let me go to blue, can be rewritten. A sub t is equal to, so the summation, as we get the summation of an infinite number of rectangles, we can write this as the definite integral from a to b of f of x dx. So the f of x sub I right here is basically becoming our function right here. The delta x becomes our dx, and then all of the limit as n approaches infinity of the summation of all these rectangles becomes our integral. And so this is the definite integral. And again, this is just a real quick review of what you learned in Calc 1. This isn't meant to go into this in great depth in this video. What I'm trying to do is just show you the important relationship between a definite integral, the Riemann sum, and the area under a curve. Because when we get into Calc 2 material, we're going to look at the area between two curves. And I'm going to start this out by showing you rectangles. When we do volume, we're going to be looking at rectangles. And so I want you to be able to make this important connection up here between the area under a curve using rectangles, the Riemann sum, and then the integral, the definite integral. So to do one quick example that you might do in a Calc 1 class, so let's say we want to find the area under the curve of the function f of x is equal to 16 minus x squared. Now when we say the area under the curve, let's say and above the x-axis. Okay, so area under the curve and above the x-axis. So again, if we were to draw a little sketch of this, and you can do this in Desmos, but that's basically the graph that I had just showed you. Here's my f of x. And so this point right here is going to be 4. And so we're looking for all of this area under the curve but above the x-axis. Well, that area, we don't have to actually do a Riemann sum. We can just use the integral from 0 to 4, because this is 0 right here, of my function 16 minus x squared dx. And so what we want to do is take the antiderivative. So the antiderivative of 16 is 16x. The antiderivative of x squared is 1/3 x cubed. And then we're evaluating that from 0 to 4. And so the area is going to be using 16 times 4 minus 1/3 times 4 cubed. I'm using the fundamental theorem of calculus now, f of b minus f of a, times 16 times 0 minus 1/3 times 0 cubed. Alrighty, so what does this all end up being here? So area is equal to, well, 16 times 4 is 64, minus 4 cubed is 4 times 4 is 16 times 4 is 64. So this is 64 thirds. That's my f of b. And when I say f of b, remember that when you're evaluating an integral, you use the fundamental theorem of calculus, which is f of b, the antiderivative at b minus the antiderivative at a. And then this is all just 0. So the answer is 64 minus 64 thirds. So what's 64 times 3? It's 180, 192, 192. I hope I did my arithmetic in my head quickly correct. Over 64 over 3. And so if we subtract those, we're going to get 128, I believe. 128 over 3. Yeah, 28. Yep. And so that would be my answer. So the area under the curve is 128 thirds. And of course, you would want to change that probably to a decimal number. Now, I've showed you in class how you can go through and you can take your original integral. This would be the original integral. And you can set it up in Desmos. Whoa. You can set that up in Desmos to get the actual number as a decimal. Now, you still need to be able to go through and find the antiderivative and evaluate it, but go ahead and use Desmos to verify that answer. All right, so again, this is just a quick review of the relationship between the area under a curve, a Riemann sum, the definite integral and the fundamental theorem of calculus. All right, I hope you found this to be somewhat helpful.